Welcome to this video looking at all the topics you need to know for GCSE Physics Paper 1. So this is suitable for all students, foundation tier, higher tier, combined science, separate science. We're going to start off with energy stores. So you can see the 6 main energy stores I've listed here. Anything that's got thermal energy could be anything that's hot, anything above absolute zero, for example an oven, but lots of examples really. Chemical energy you'd find in batteries, food and fuel. Kinetic energy is in anything that moves, so a car or a person running. Gravitational potential energy is anything that's got a height above the surface of the Earth, so for example a ball being thrown. Elastic potential energy would be contained in elastic bands and springs, and nuclear energy, the only real example of that for GCSE is in uranium fuel in nuclear power stations. The conservation of energy, or law of conservation of energy, states that energy cannot be created or destroyed, only transferred from one form or one store into another. So for example, on these energy stores, if one goes down a bit, another goes up a bit. Now, really importantly here is this only applies in what's called a closed system. A system is an object or a group of objects, so if it's closed, it means there's no energy can come in or out. Now, some of these energy stores are lucky enough to have their own equation. So we've got an equation for kinetic energy, for elastic potential energy, and for gravitational potential energy. So obviously you do not need to memorize the equations anymore, but you do need to know the units and how to use them. So the units for kinetic energy are joules. Mass is always measured in kilograms, not grams. Speed or velocity, that's why it's a V, is measured in meters per second. For gravitational potential energy, it's joules again. Gravitational field strength is measured in newtons per kilogram. That is almost always in your questions going to be 9.8 if you're on planet Earth. And change in height has to be in meters, not centimeters or kilometers. Elastic potential energy, we've got something called a spring constant, which comes up more in paper 2 when you look at springs in more detail, but it's measured in newtons per meter. And extension, how much something extends by or compresses by, is measured in meters. Now, I mentioned that you don't need to memorize the equations, you do need to know how to use them. So I'd strongly recommend using something like a method called FIFA. FIFA stands for formula, insert your values, fine tune, and then give your answer. The idea is not to use formula triangles, not to guess whether to divide or times, but by doing this step. And you always get the first mark, even if you go wrong later on. So I've got an example here. It says find the height dropped if a half kilogram ball loses 50 joules of energy, gravitational potential energy here, and G is 9.8 newtons per kilogram. So what we do is we write out our formula. Hopefully it's obvious which one we're going to talk about. We're talking about gravitational potential energy, so M times G times change in height. Insert my values. I've got underneath the energy, I've now got 50 joules. Underneath the mass, I've got 0.5, G is 9.8, and the change in height I don't know, so I'm going to leave that as an X, or you could leave it as a H or a question mark, whatever. You just don't know what it is. Next, the fine-tuning stage. We need to make sure we are making life simpler for ourselves, so therefore 0.5 times by 9.8 is 4.9, just makes the equation look a bit easier, and hopefully we can figure out from there to get rid of the times by 4.9 to find x. I divide 50 by 4.9, which in this case gives us an answer of a height or change in height of 10.2 meters. Our second example is a little bit trickier. This is an example of a multi-step equation, which I'll link a whole video I've done on these type of questions in the video at the top right. So this question says a roller coaster car is at a height of 150 meters, has a mass of 2,000 kilograms. What can its maximum speed be at the end? Now at the top, the roller coaster is going to have a velocity of 0, so it's stationary. It's going to have a lot of gravitational potential energy. But to work out its speed, we need to make a little assumption here, which is that all of its potential energy gets converted into kinetic energy. Obviously that wouldn't happen in real life, there'd be energy lost. We'll talk about that a bit later. So if we work out its gravitational potential energy first, so that's 2,000 times by 9.8 times by 150 gives us 2,940,000 joules. We can then say, well, if that's all get converted to kinetic energy, therefore in the kinetic energy equation, there's that number equals a half times by 2,000 kilograms times by the speed squared. So to get the speed squared by itself, I can do a half times by 2,000, easy peasy, that's 1,000, and divide 2,940,000 by 1,000, and then to get rid of the v squared, to make it v, I've got to do a square root at the end, which gives me 54.2 meters per second, which is pretty fast, but it is a roller coaster, so not too unreasonable. Now, some of you might notice you could actually cancel the m's in both equations because a mass is in both equations. However, stage by stage at GCSE, just make sure your marks, I would include it in your workings. An object or system is said to be doing work if it is transferring energy. So example, our roller coaster earlier was transferring energy to thermal energy store due to friction. You could also say it's doing work overcoming friction. It means the same thing. There is a separate equation for work done, which is work done equals force times by distance. Work done is in joules, also giving us a hint that it's the same thing as energy. Force is measured in newtons and distance is measured in meters. Power is the rate at which energy is transferred, or again, the rate at which work is done. It's got two different equations which are equivalent to each other. It's either energy divided by time or work done divided by time. Either way, power is measured in watts and time has to be in seconds. Efficiency is a measure of how usefully energy is transferred. The higher the number, the more usefully energy is transferred. To calculate it, you need to know the useful energy output divided by the total energy input. And you can either leave it as a decimal or times by 100 to make it as a percentage. Now, instead of energy, you could also put power into this equation. It doesn't really matter. There are two equations on your equation sheet. Just keep an eye on what you're given in a question. To improve the efficiency of a machine or a system, you can do a number of things. You can either lubricate moving parts, which reduces friction, just like car engine oil. You can try and insulate it as much as possible to reduce heat being transferred out, or you could try and streamline the shape, which might reduce drag. Overall, most energy is lost due to thermal energy. A good phrase to learn is it dissipates into the surroundings. As this happens, it gets less and less useful the more it is transferred. Let's talk about another one of these energy stores. Let's talk about thermal energy. So thermal or heat energy always travels from hot to cold. So a mug of tea will radiate heat outwards, and ice cream will have heat inwards, so it can melt. Sounds like a really obvious point, but often students get this mixed up. In a fridge, for example, your food is hotter than the fridge, so the heat transfers from your food into the fridge and then through the back of the fridge to the surroundings. The rate of thermal energy transfer depends on three things. This thing called thermal conductivity, the thickness of the material, and the temperature difference. So temperature difference, I think, is one of the easier ones. If you've got a house on a cold day and it's 20 degrees inside, there's going to be a greater rate of heat transfer than if the outside temperature was more similar to the temperature inside the house. So a greater temperature difference means a greater rate of heat transfer. For a thicker material, that means you have a lower rate of heat transfer because there are more particles for the heat to get through via conduction, where the particles are vibrating and passing on their vibrations. The trickier one is thermal conductivity. The clue is in the name a little bit, is to do with conduction. Let's say I've got these three materials here when I'm looking at their different thermal conductivities. So as we can see, the highest number is sand, the lowest number is cotton wool. What that tells us is that the best insulator is cotton wool because it has the lowest thermal conductivity, which means it has the lowest rate of heat energy transferred. The worst insulator, or the best conductor, would be sand, as it has the highest rate of heat transferred. The last thing for this topic is specific heat capacity. This is defined as the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree. It's got an equation on your equation sheet. Energy is in joules, mass is in kilograms. This funny symbol at the end is delta, and we use the theta for AQA for temperature change, which is in degrees Celsius. The units for specific heat capacity are quite tricky, but you can use the equation to help you. They are in joules per kilogram degrees Celsius. So if you rearrange the equation, you can find that out yourself if you remember the units of the other three things. What this means is that a higher specific heat capacity means a substance can store more energy for less temperature increase. If it's not increasing much in temperature, even though you're putting the same energy in as something else, it means it's got a higher specific heat capacity. There is a required practical to do with this as well as the insulation topic. Again, I'll just link at the top of the video so you can see in detail how to do that. Let's talk next about energy sources. So not energy stores, but energy sources. Where do we get sources for energy to provide our houses with electricity? So there are two main categories. We've got non-renewable sources, which will eventually run out. They are made up of the three fossil fuels: coal, oil, and natural gas, and also nuclear, which is not termed a fossil fuel, but it is non-renewable because there is a limited amount of things like uranium and plutonium to provide nuclear fuel. So the main benefits of fossil fuels, they are very reliable. They will produce a continual output of electricity from the power stations, and also the technology for the power stations already exists. It's already in use all across the world. That is a plus point. The downside is that they produce greenhouse gases, mainly CO2, carbon dioxide, which will increase global warming. Nuclear energy does not produce carbon dioxide. Its main pro point is that it is going to produce more energy per kilogram. Not more energy, but compared to 1 kilogram of coal, it produces about 1,000,000 times more energy. It does, however, produce radioactive waste and is therefore very expensive to decommission to get rid of all that waste. The same arguments apply with fossil fuels with cars and houses. Using less is much better for things like transport and how we heat our houses. Now, renewable energy sources won't run out. They're made up of these 7 different types of renewable energy source you see here: solar, wind, wave, biofuel, geothermal, hydroelectric, and tidal. Now, the main benefits of these are the opposite of non-renewable sources. They do not produce greenhouse gases, apart from biofuel, but that's still carbon neutral, and they do not contribute towards global warming. The downsides are they're not as reliable generally, especially these 3 on the left. So solar, wind, and wave power all rely on the weather. It's not always sunny, it's not always windy, and therefore there's not going to be as many waves as well. So biofuel is anything that involves organic matter. So plant oil, cow dung, wood chips, all that stuff can be burnt to make electricity from farms. And the downside to that is that it emits carbon dioxide. In geothermal power plants, and that uses heat from the ground, and that's only available in some locations where there is lots of volcanic activity. Hydroelectric electricity is a downside of that is that floods. There are lots of habitats destroyed when you build these giant hydroelectric dams. As a quick reminder, you've got hydroelectricity is from a reservoir of water up high going downstream. We can harness the kinetic energy that produces when it turns a turbine. Tidal power has the same issue, but is different to wave power. People often get confused. It does not rely on the waves, it relies on the tides, which are quite reliable twice a day. All these energy sources can be used to provide electricity in the UK via the national grid. The national grid is a network of cables and transformers linking power stations to consumers. So in this diagram here, we've got the power station on the left, we've got the consumer on the right. Now, after the electricity is produced at a relatively high voltage by the power station, it is increased to a really high voltage, often hundreds of thousands of volts, by something called a step-up transformer. So the reason it does this, it increases the potential difference or the voltage because it is trying to decrease the current. When it decreases the current, you actually reduce the heat loss to the surroundings and therefore improve the efficiency of the whole system and generally then save people money. The step-down transformer reduces potential difference to 230 volts, so it is safe for domestic use. That is the phrase to learn. Do not say it'll blow up or it'll shock people. It is just safe to use in homes. Now, all these things are used to meet what's known as the electricity demand. That's how much energy people require and how much electricity they require. Now, this varies with time of the day. It is we use the most electricity in the evenings when people are cooking food, turning lights on, coming home from work, and time of the year depends as well. So if it's a cold time of the year, we're going to use more electricity, generally speaking, because people are staying in their homes as opposed to going outside. GCSE students can often find the topic of electricity quite a tricky one. So we're going to start off with the basics. You need to know all these different circuit symbols. There are trickier ones towards the end. We're going to cover what they do, but we should be familiar with switches, open and closed, and the rest of them down the left-hand side. So what we're going to look at first is these 2 ones at the top right here, voltmeters and ammeters. Now, a voltmeter will measure potential difference in a circuit. So potential difference, or PD, is exactly the same thing as voltage, but exam questions will use the word potential difference, so make sure you're familiar with it. Now, the definition for potential difference is the work done per unit charge. Now, we can know this definition by looking at an equation. One of the equations on your equation sheet is E, energy transferred in joules, or work done, equals potential difference in volts times by charge in coulombs. If I rearrange this a little bit, I've got V equals E over Q, which is work done or energy transferred divided by charge. An ammeter will measure current. No, it doesn't measure amps, it measures current. Amps is the unit. This is defined as the rate of flow of charge in a circuit. Now again, we've got an equation that goes with it. The equation is Q, charge in coulombs, equals current in amps times by time in seconds. If I rearrange this for I, the current, I will find that it equals to charge divided by time, which is the same thing as saying rate of flow of charge. Don't forget, rate just means per second. Now, inside a circuit, for any current to flow, there must be a potential difference. So for these electrons here in orange to go through a wire, there must be a positive charge sort of attracting them through the wire for them to be able to flow. Otherwise, they're not going to go anywhere. Now, as these electrons go through the wire, they can encounter some resistance. Now, what resistance is in a wire can be caused by numerous different things. Sometimes it's the material, sometimes it's the temperature, but a higher resistance means a greater opposition to the flow of current. So if there's a higher resistance, that means there's a lower current. The technical relationship between the two is to say they are inversely proportional. If one doubled, the other would half. Now, for certain components, they follow something called Ohm's law, which is to say that potential difference is directly proportional to the current flowing, assuming all conditions like temperature are constant. If I was to plot a voltage current graph of them, I'd find that it's a straight line through the origin, and if I was to find the gradient of that graph, that would tell me the resistance. The equation says that potential difference in volts is equal to the current in amps times by resistance, which is measured in ohms, and this applies for something that follows Ohm's law or an ohmic conductor. To practically investigate these characteristics of how voltage or potential difference and current vary, we need to construct a circuit a bit like this. Now, this is part of the required practical VI characteristics or current voltage characteristics, which I've made a separate video about. But in this circuit, we'll go through the basics. We've got an ammeter and a voltmeter to measure the current and the PD. We've also got a variable resistor. Now, as the name suggests, this is going to be able to change the resistance in the circuit, but that also changes the current, which is one of the things we're measuring, and it will also change the PD. We need to know for 3 different components what the current voltage or current PD graphs look like. Now, to be able to do this, we need to find out also what their negative readings look like. So to find that out, all we do is just reverse or flip over the cell to obtain negative readings. So the first component is the resistor, which we've already looked at. That's going to follow Ohm's law, so be directly proportional. PD and current will be a straight line through the origin. The next component we're going to use is a filament lamp. Now, filament lamp is one of these old school type lamps or bulbs, as you see in the picture here, not a new LED one. Now, the curve for this graph looks a bit like this. So initially, it's going current is increasing at a very slow rate, then it increases quite a fast rate, and then goes to a slow rate again. So the explanation for this is all due to what happens when you increase the potential difference across a filament bulb. So as you increase the potential difference, the temperature increases. These old types of bulbs get really hot quite quickly. When that happens, that increases the resistance in the filament. This is due to the ions, so there's positive charges left behind, are vibrating more, so it's harder for electrons to get through. As this happens, the current stops increasing. Note the current doesn't go down, the curve just sort of flatten out a bit, it stops increasing. The third component we're going to look at is the diode, which this would also apply for a light emitting diode because it's just a type of diode. If I'm to plot the graph here, a very weird thing happens. In one direction, the current is zero, totally zeroed the whole time. However, if I reverse the cell, we'll notice after a certain voltage, the current increases by quite some amount. Now, this tells us what a diode does. A diode allows current to flow in one direction only. It's just like a valve in the heart. The reason for this is because it has a really high resistance in the opposite direction. So they're designed for current to flow in just that one direction. And the direction is important here as well. The way I've drawn it in the circuit is correct. We draw a diode with the play button, the triangle pointing in the direction that conventional current is flowing. So going from positive to negative. So if you follow the positive symbol on the cell, it's going in this case around down, past through towards the right of the diode, and not the other way. The last 2 components we're going to look at are the thermistor and the light-dependent resistor. So in a thermistor, when you increase the temperature across it, normally in a wire, the temperature increases, the resistance increases, as we just discussed. However, in a thermistor, the temperature goes up. That means the resistance actually goes down. They're made out of material that has a reduced resistance with more temperature, meaning current, I, can increase. Now, this is useful in thermostats, like in thermostats in your home, to detect a change in temperature and change a circuit accordingly. A light-dependent resistor, or LDR, is very similar, but this time it responds to change in light. So an increase in light would mean the resistance goes down, and the same thing happens, current would increase. This is used in street lights, which respond to a change in light level in the evening to be able to switch on. There are two types of circuits, series and parallel circuits. In a series circuit, the current follows one path and the circuit looks like one big loop with components in series, one after the other. In a parallel circuit, you can add a path in parallel with each other, meaning the electrons can take multiple paths around the circuit and you have several loops. It doesn't have to be 2, it could be 3, 4, 5, whatever really. We need to know how the current and PD vary depending on what circuit we're using. So for a series circuit, if I was to put an ammeter at different points throughout the circuit, current does not get used up, so the current is the same at any point. If I was to do the same thing with a parallel circuit and have ammeters at the start and on each branch, what we'd notice is that there is more current nearer the battery and there is less on each branch. So this shows us that current is shared between the paths or between the branches. If I was to have 2 amps going in initially, then I'd have 1 amp shared, assuming the resistances of the bulb are equal. Let's look at potential difference. In a series circuit, this is shared between components, meaning if I use 3 volts of 6 volts up at one bulb, I'm going to have 3 volts left for another bulb. They don't have to be equal, in this case there are. A potential difference in a parallel circuit is the same across each path. So the reason for this, if it's 6 volts at the battery, each electron gains 6 volts. As the electrons go around the circuit, they either travel through the first path, so the middle path here, or they travel through the bottom path. None of them travel through both, so they give up 6 volts of energy per unit charge to their component and then go back to the battery. There's one big advantage of parallel circuits over series circuits. In a parallel circuit, if one of the bulbs breaks, that means that you've got another bulb that can still be lit because the electrons can still reach that bulb. If one component breaks in a series circuit, because they're all in series, there is no current that flows and the circuit is broken. Now resistance, understanding resistance in series and parallel circuits can be quite tricky. In a series circuit, you just add the resistances together. So in this case, I'd have 5 ohms plus 15 ohms would be 20 ohms. In a parallel circuit, it's a bit different. You can't be asked to calculate it because that's A-level physics content, but the rule is that the total resistance is always lower than the value of the lowest resistor. So let me explain what I mean. If I've got the top loop of the circuit intact with just my 5 ohm resistor, by adding an additional branch, I'm actually increasing the current that can flow in the circuit because there are more paths for the electrons to take. If you increase current ever, that means you are decreasing the resistance. So adding more resistors in parallel actually decreases the resistance. And in this case, all we'd know is that it would be lower than 5 ohms. Plugs in the UK look a bit like this. We've got 3 different wires and a fuse. So the brown wire is known as the live wire, the blue wire is known as the neutral wire, and yellow and green indicates that it's an earth wire. The way to remember which way around the wires go is that brown has got an R in it, so that's always on the right, blue has got an L in it, that's always on the left, and then the earth wire is the one in the middle. So what happens between a live wire and a neutral wire is that the live wire has a potential difference flowing through it of 230 volts. Neutral wire has 0 potential difference. So there's a potential difference between those 2 different wires of 230, which is what drives the current to flow to power appliances in your homes. The purpose of the earth wire is to carry any dangerous charge to the ground to prevent electrocution. This would only happen if the live wire accidentally touches the metal case of an appliance. If there's a plastic appliance, the earth wire is pretty redundant, not needed here. Another safety feature is a fuse. So a fuse contains a fuse wire which melts when the current gets too high, and this breaks the circuit altogether, so therefore meaning the fuses will not get too high. In the UK, that potential difference value is constant for all plugs and all appliances are designed to run from 230 volts. Now, the frequency that is provided by the mains electricity is 50 Hz, meaning the direction changes 50 times every second. This happens because it uses something called alternating potential difference. Potential difference that's alternating means it changes polarity or reverses direction. Polarity just means going positive to negative or back. Direct potential difference doesn't change direction, and do be careful, in the AQA specification it does only talk about alternating PD, not alternating current, so I'll ask about alternating PD. To get an electric shock, if one of these things doesn't work inside the plug, that means there has to be a very high potential difference between two objects. So that means that current or charged electrons can move between the two objects, causing the electric shock. Inside any electrical circuit, there is going to be some electrical power supplied by a battery or a cell. Now, the definition of power is the same as from the energy topic, which is the rate of flow of energy transferred, but we can also use it to calculate the energy supplied to a device. If we knew the power rating of the appliance, we multiplied that in watts by the time taken in seconds, we would find the energy supplied to the appliance in joules. So in this quick example here, if I've got two microwaves, one's operating at 800 watts, one's at 1000 watts, but the same plate of food in each, which one is going to heat up the food first? So given that the energy needed to heat up each plate of food would be the same because they're identical, the one with the higher power rating would be able to heat it up in a lower time, so therefore it would be the 1000 watts power rated microwave. To calculate electric power using the current and the voltage, we need to multiply them together. So power equals current times by PD. Now you can derive this from the power equals energy over time equation. It's just a different way of expressing, it's just a different way of calculating the power using current and PD. If we substitute into this equation the fact that voltage PD equals current times resistance, we could come up with a new expression, and it's the last of the electrical equations, which is that power equals current squared times by resistance in ohms. And this is commonly known as the rate of energy lost through heating. Rate meaning per second, energy is just energy, so energy per second lost through heating you can often work out as multiplying I squared times by R. Now, almost all electrical appliances will lose energy due to heat at some point. This is due to the fact to make electrons flow through a wire, even if they're made of the lowest resistance material, even if it's really good high-grade copper, there's always going to be heat loss due to friction created when electrons move through a wire, causing the ions in the lattice to vibrate, just like for the filament bulb, meaning heat is going to be given off. The last little bit of content for the electricity topic is only if you're doing triple physics or separate physics, so you don't need to know this if you're doing the combined science course. Now, an example of this might be if you're bouncing on a trampoline or going down a slide that is made of plastic, rubbing two insulators together, electrons get transferred from one surface to another. Now, when this happens, it is the electrons that move, not positive charges. But when you take away electrons, which are negatively charged, you are going to have a positive charge left behind. So another example of this would be if you rubbed a balloon on your head for a while, the balloon might gain a negative charges, your hair would have less negatives, meaning it's positively charged. If you have a negative and a positive charge together, they're going to attract. However, if you were to find that you had two like charges, like two positive charges, they would repel. Electrostatic force is a non-contact force, and electric fields provide the non-contact force look a bit like this. Around a positive charge, the field lines are pointing away. Around a negative charge, they're pointing towards it. If you have a higher concentration of field lines, it means that the field is stronger. So in this case, the positive charge is stronger. Let's say it might be positive 7 coulombs, and the negative might be minus 4 coulombs. The stronger the field lines are close to the center of the charge because there are more field lines, and that means if you move further away, the field strength decreases. States of matter often seems like it's the easiest topic to revise, but trust me when I say you have to be really precise with your language, otherwise you're going to lose easy marks. So when we're drawing out particle diagrams, make sure the particles are the same size, make sure the liquid particles are touching, and the solid particles are in clear rows or columns. Now we're going to look first at the properties of solids, liquids and gases, then how do we go about explaining them in a 6-mark answer, for example. So comparing like properties, the shape of each material is slightly different. In a solid, we've got a fixed shape, it doesn't change shape. A liquid can flow to the bottom of a container, and a gas can fill an entire container. Next, we're talking about their density. So a solid has a very high density, liquid has a fairly high density, whereas gas have very low density. A reminder that density is equal to the mass divided by the volume. If you want a bit more detail on how to find the density of different materials, check out my video on the required practical you also need to know for paper 1. The next property is its compressibility. So a solid is incompressible, it cannot be compressed. The same applies to a liquid, but a gas can be compressed or squished, in other words. So next what we're going to look at is how to describe how particles can help explain those different properties. And this is quite commonly referred to as kinetic theory, and basically means how do particles help explain these properties with their behavior. Quite often questions will just say particles though, make sure you put part of the word particles in your answer. The first thing we're going to talk about is the spacing between the particles. This is quite an obvious one, but in a solid there is no spacing or minimal spacing between particles. In a liquid it's the same, they should be touching, and in a gas they are spread out. The movement of the particles, solid particles do move, don't fall into the trap so they don't move, but they vibrate about a fixed position, meaning they go back and forth but never have an overall change of position. Liquid particles move freely, gas particles move freely as well in random motion at a range of speeds. The arrangement of particles comes up quite a lot in papers. In a solid, the particles have a regular pattern. You could say they're in rows and columns. In a liquid, there is no pattern or an irregular pattern, and the same applies to gases. And the last thing we're going to look at is the forces of attraction, or the bonds between particles. Solid particles have very strong forces of attraction between them, and in a liquid the particles have very weak forces of attraction. In a gas they have no force of attraction at all, mainly because they're so spread out there's no possibility for those bonds to exist. So in a 6-mark question, quite often they will ask you to link the properties to the kinetic theory, or how the particles behave. So we're going to have a look now at how these different features about the particles in each state of matter help explain their properties. So the first one I'm going to look at is its compressibility. Solids and liquids are incompressible because there's no space between the particles, whereas gases are compressible because there is space between the particles, or they are spread out. Now, the shape of a solid is due to the fact that the particles are only vibrating about a fixed position, and they have strong forces of attraction. In a liquid, they can flow because the particles can move freely because there is very weak forces of attraction, and the same thing applies for gases. They have no forces of attraction, so they can move freely, randomly, so therefore they can flow to fill the container. Now, we can use the spacing to help explain the density behind a solid. If they're all packed very close together, a high mass in a very small volume, that's due to the fact there's no spacing between them. They're also in a regular pattern to allow them to do that. In a liquid, again, there's no spacing between them, so they have a high density because they have a very low volume for their mass, whereas in a gas, you have the particles are very spread out, so a high volume, which means a lower density. The arrangement of particles could come up in lots of different questions, but just make sure you know to describe the pattern as being regular or irregular, depending if it's a solid or a liquid or gas. Let's talk next about changes of state between these states of matter. So we should all know a solid to a liquid is known as melting, a liquid to a gas is known as evaporating. Going the other way, we've got a gas to a liquid is condensing, and a liquid to a solid is freezing. To be able to go from a solid to a liquid, or to a liquid to a gas, that requires an increase in energy, or energy to be supplied. Whereas to go the other way, gas to liquid or liquid to solid, the substance is going to decrease in energy, meaning it's going to release energy to the surroundings. All these are known as physical changes of state, meaning that there are no chemical changes or changes to the chemical structure of the material. Just like ice melting, you can get the ice back. And mass is always conserved, meaning it's the same before as it is after. Next, let's talk about a really commonly misunderstood topic in this paper, which is that of internal energy. So a substance's internal energy is made up of the particles' kinetic and their potential energy. So kinetic energy we should be familiar with means movement. So in this case, it's the movement of the particles. Now, if particles have a greater movement, so they're vibrating more or they're moving around more, that means the temperature of the substance is greater. The less commonly understood one is the potential energy. This relates to the spacing of the particles, how far apart they are. The higher the spacing of the particles, the less their potential energy. So we can start to add some of these extra properties into our solids, liquids and gases. So the lowest potential energy, because they're the furthest apart, is a gas, whereas the highest potential energy, because they're the closest, is a solid. Conversely, the highest kinetic energy is held by particles in a gas because they have the highest speed, the highest movement, whereas the lowest kinetic energy is in a liquid because even though the particles are moving, they're not vibrating very much overall. Now let's look at an example of how these different internal potential energy changes as a substance is heated. So we're going to use the example of ice. Imagine you had a bunch of ice in a cup or a beaker with a thermometer to measure the temperature, and you were able to supply heat from a Bunsen burner or something like that. What we're going to look at is how the temperature changes with the energy supplied and how the kinetic or potential energy changes as well. So initially, as you'd expect, with more energy supplied, the ice will become warmer, then it will melt, then it will become a liquid, then it will evaporate and it'll become a gas. Now what we should notice is that while the temperature increases while it's a solid, liquid and gas, between these states when it's melting or when it's boiling, it is got a constant temperature. That constant temperature is known as a melting point for the melting stage and a boiling point for when it is evaporating. So why is it then that the temperature is constant at these stages? I'm just going to redraw this graph slightly to color code it, just so we can compare the two different situations. Now, when the temperature is increasing, when it's a solid or a liquid or a gas, that is relatively straightforward. All the energy is being transferred to the kinetic energy of the particles, meaning they have higher speed, meaning the temperature goes up. For all the parts where it's changing state, where the temperature is constant, that is because the kinetic energy is not changing. As the temperature is constant, all that energy is going into potential energy, which is going to be changing the spacing of the particles as it is changing state. This energy is being used to break the forces of attraction or break the bonds between particles, and there's no more left over to increase the temperature. So the particles do not increase their movement, they just break apart at those instants where it's melting or evaporating. Latent heat is defined as the energy needed to change the state of 1 kilogram of a substance. So this would occur at the purple points in the graph when it's either melting or evaporating. There are two very technical names given to the two stages it could be. So for a solid to a liquid is known as latent heat of fusion, and from a liquid to a gas is known as the latent heat of vaporization. Gas particles can be responsible for exerting pressure in a gas, like in a tyre in a car or a bike. They do that because when the gas particles collide with the wall of the container, they exert a force. Now, when that force is in a specific area, we call that pressure. Pressure is known as force per unit area or force divided by area, which is where pressure comes from. In a gas, the temperature is directly proportional to the pressure, meaning that if I increase the temperature, the pressure is going to increase at the same rate. The explanation behind this is that at higher temperature, particles in a gas have a greater kinetic energy, or they have a greater speed. Now, because they have a greater kinetic energy, they are able to have more frequent collisions with the container. We could say more collisions per second. Don't just say more collisions, it's got to say more frequent. And they also have a greater force because they're traveling at a higher speed. So with that said, more frequent collisions and a greater force means that it's going to be a higher pressure, as we just talked about. The other thing that can change the gas pressure is to have a greater number of particles, like pumping air into your tyre will increase the pressure because there are those more frequent collisions because there's more particles. The last part of this video is going to be talking to separate science students or triple students only, so you do not need to know this if you're taking the combined science course. So the last thing about this topic is to look at how pressure and volume of a gas are related. They're related by saying pressure is inversely proportional to the volume of a gas, given by this expression here. If I was to plot a graph, it would be a curve decreasing like this. If I wanted to prove that they're inversely proportional, I need to multiply values of pressure and volume together, and they should be a constant value, meaning that if they're inversely proportional, if the volume was to double, the pressure was to halve. The explanation behind this is that at a smaller volume, there are less space for particles to move. So therefore, you're going to have more frequent collisions between them and the container wall. More frequent collisions means more force, which means more pressure, as we've just discussed. To understand radioactivity, we need to understand atoms. So we should all be fairly familiar with a diagram like this, which shows us a model of the atom. We've got protons with a positive 1 charge and a mass of 1, neutrons with a neutral charge of 0 and a mass of 1, and electrons have a negative charge and a relative mass compared to the other two of 1 over 2000. Now, it's important to note this diagram is very much not to scale. The electron should be a lot smaller, but also the size of the atom we need to know is about 10 to the power minus 10 meters. A nucleus is even smaller, about 10,000 times smaller, which will give it a rough diameter of 10 to the power minus 14 meters. So how did we get to this point? Let's have a look next at the development of the atomic model and how it developed over time with new evidence. So one of the earliest ideas of the atom was that it was a solid sphere. So that means that it's indivisible, it can't be divided up further. This idea persisted up until around the late 1800s when electrons were discovered. So with electrons being discovered, that means they've got a negative charge, there must be a positive charge in the atom as well. So one of the early models that explained this was the plum pudding model put forward by J.J. Thomson. He said that the atom was like a plum pudding, which is sort of like a chocolate chip muffin. You've got this ball of positive charge, which would be the muffin, and then you've got these electrons distributed evenly, which would be like the chocolate chips. Now, the next thing that came along to cast doubt on that was the alpha scattering experiment, which was done by Ernest Rutherford. Now, this led to the development of the nuclear model, which had a positive nucleus, which was small and dense, and had electrons that were negative orbiting around the edge of the atom. And in between, there was mostly empty space. Most of the atom was empty space. Now, this seemed like quite a radical idea at the time, and it could only be put forward due to very strong evidence from the alpha scattering experiment. So the alpha scattering experiment fired alpha particles via an alpha source at a thin gold leaf, and it had a big detector on the other side to see where the alpha particles went. Now, this had to take place in a vacuum, so there was no collisions with air molecules that would disturb the experiment. The evidence it discovered was that almost all the alpha particles went straight through the gold leaf, which was kind of as expected. That would have happened if the plum pudding model was correct. However, some of the alpha particles were deflected by the atoms in the gold, and very few, 1 in about 10,000, were deflected by really large angles. So when we say angle, we mean the angle that the beam would make compared to if it went straight on. So these large angles basically meant it would bounce back and come the other way. So let's look at next. So what did that evidence lead Ernest Rutherford to conclude about the atom? So the fact that most alpha particles went straight through, he concluded that most of the atom must be empty space. The fact that some of them get deflected by atoms in the gold led him to conclude that there must be a positive region, a quite dense positive region, which had enough charge to deflect alpha particles. Now, alpha particles deflect because they have the same charge as the nucleus. So for them to come close together, that would mean they're going to repel because they have the same charge, and like charges repel. The closer they go to the nucleus, the greater the force they're going to experience. Now, the other conclusion was that the nucleus must be very, very, very small with all the atoms positive charge there, and they would explain the idea that very, very few of these particles would deflect straight back or at a very large angle. Because they're getting so close to the nucleus, they experience a stronger force, which is going to have a larger deflection, as seen in the diagram here. So when the alpha particles come close to the nucleus, this is what happened. This was unexpected. With the plum pudding model being correct, they would expect all the alpha particles to go straight through. Now, this was because even though there were positive and negative charges inside the atom, that they're so evenly distributed and the negative charges are so small that actually it would have very little effect on those alpha particles. A really important part of the development of the model of the atom is the idea of evidence. So this is a really good example of new evidence coming to light via an experiment that does not support the plum pudding model theory, and it does support or lead rise to a new theory, which was the nuclear model. Please don't say things like it gets disproved or things like that. There's only evidence that can be provided to support a model. Now, we might notice in a nuclear model, the electrons are orbiting sort of all over the place around the nucleus. The next development was Niels Bohr, and this leads to the Bohr atom. In the Bohr atom, it is very, very similar to the nuclear model, but the electrons are orbiting at fixed orbits or in shells around the atom, where they cannot just orbit anywhere. Another thing the Bohr model was able to explain was the idea that electrons can change between electron shells. So if an atom absorbs electromagnetic radiation, then what that allows it to do is that the electron can move to a higher energy level or a higher energy shell. So it gets promoted to the next level up. Conversely, if the electron goes back down to a low energy level, that results in electromagnetic radiation being emitted or given off. This is an example of energy conservation, where EM radiation being given off means the electron has lost energy, so the energy gets emitted as EM radiation. The last little step on our journey is the neutrons, which were discovered quite late, quite a couple of decades after the nuclear model. This is because they have no charge, they're very difficult to detect. And this was done by James Chadwick, who discovered the neutron and led to the atom looking like it does on the right-hand side of the screen as our model. Next up, we're focusing specifically on the nucleus, in particular, how to work out how many protons and neutrons are inside a nucleus. So in this example here, I've got some carbon-12. As you can see from the diagram, we count them up. There are 6 protons and there are 6 neutrons. So the atomic number is the number of protons. So in this case, that will be 6. The mass number, the bigger number usually at the top of the element symbol, is the number of protons plus the number of neutrons. So in this case, that happens to be 12. To work out the number of neutrons, you do the mass number minus the atomic number. Now you can have the same element, in this case carbon, with a different number of neutrons. So if I add 2 extra neutrons in here, so that it's now got 8, the mass number will change to 14. The isotope is defined as an atom that has the same number of protons but a different number of neutrons. So in this example, 2 isotopes of carbon would be carbon 12 and carbon 14. Note that the element is the same because there's the same atomic number. And because of this, they must both have the same charge in the nucleus because they've got the same number of protons. For an atom to have a different charge, it's called an ion. An ion is defined as an atom that has gained or lost 1 or more electrons, just like you would have learned in chemistry. Normally, for an atom that is not an ion, you're going to have the same number of protons as there are number of electrons to make the atom balanced in terms of charge. But with an ion, the electrons has changed, so therefore it is now got an overall positive if it's lost electrons or a negative if it's gained electrons. I've used the example of carbon 14 here because it is radioactive. So what is it that makes it radioactive? Well, any radioactive nucleus is said to be unstable. It can happen with different types of nucleus, but they all have that thing in common, they're unstable, and it's usually due to an excess of protons or neutrons. So when an atom is unstable, there is radiation emitted. Now this radiation emitted when an unstable nucleus decays can either be alpha, beta, or gamma radiation, or sometimes just pure neutrons. So how do we work out which type of radiation it is? Well, we need to have a radioactive source, and we need to have something to detect the radiation. That's called a Geiger-Müller tube, or a Geiger counter, set up close to the radioactive source. The Geiger-Müller tube is hooked up to a counter, which is going to measure the count rate. The count rate is defined as the number of decays measured per second. At the radioactive source, the number of decays per second is called the activity. That's the number of decays in the actual source per second, and that's measured in becquerels or BQ. Now it's important to note the difference between activity and count rate. They both look like the same definition, but the count rate is the number of decays per second that are measured, whereas the activity is the actual number of decays per second. That's because some of the radioactive particles or waves will go outside of the detector and won't be picked up. So how do we figure out which type of radiation is in our source? We use something called an absorbing material, and depending on the absorbing material, we could be able to figure out whether it's alpha, beta, or gamma radiation. So let's do a little summary table then of all the different properties of alpha, beta, and gamma radiation. We can also look at what they are, which can help us figure out what their properties are. So we're going to look at their range in air, if there's nothing stopping them. We would look at what material stops them or is absorbing the radiation. Are they ionizing or not? And also, what is it? So alpha radiation first. Now in air, if you put the Geiger-Müller tube anything greater than 5 centimeters away, it wouldn't detect it. So the range is 5 centimeters. It's stopped by anything as thin as paper, could be human skin as well, but paper is the thinnest thing, and is very ionizing. An alpha particle is made up of 2 protons and 2 neutrons. Beta particles, on the other hand, have a range of up to 1 meter in air. They're only stopped by a thin sheet of aluminium, and they are ionizing, but only moderately ionizing, not as much as alpha radiation. A beta particle is an electron. Gamma radiation can travel many kilometers. Realistically, you could say it's infinite range. It's only stopped by very thick lead or very thick concrete, and it is ionizing, but only very weakly ionizing. Gamma radiation, we might remember from the waves topic, is a high frequency electromagnetic wave, or EM wave. And neutron, we don't need to worry about the properties of here for GCSE. Now if we consider all the different air molecules, we can help explain these properties but using the idea of ionization. So let's start off with gamma radiation. Gamma is not very ionizing. What that means is when it encounters an air molecule in the air, it is unlikely to ionize it. So it's unlikely to go through all the air molecules to the other side, so it has a high range. Beta, on the other hand, is moderately ionizing, so might ionize some of these atoms, and it will lose energy each time and eventually stop after around about 1 meter on average. Alpha radiation, on the other hand, is very ionizing, so it's likely to ionize lots of atoms very close to it, meaning that it's going to lose lots of energy very quickly, so it can only travel a few centimeters in air. Let's look at the uses of each of these types of radiation and see if we can link their use to what are their properties. So alpha radiation is used in smoke alarms. This is because it's highly ionizing. It ionizes air to allow a current to flow between 2 points. When smoke particles get into the smoke alarm, that stops the current flowing because smoke particles are not charged, just like in the diagram shown here. Beta radiation is used to monitor the thickness of aluminium foil. Beta is suitable because if too much will go through, that would show the foil is too thin. If not enough go through, that may mean that it's a bit too thick. So it's only beta that can be used because some of it gets absorbed by a thin aluminium foil, but some of it will go through. Gamma radiation is used in radiotherapy. This is used to destroy cancerous cells in the body. Now, it can destroy them because it's weakly ionizing, but more importantly is that the radiation can get through the skin and into the body, unlike alpha and beta can't do that. Let's look next at nuclear equations. So we have a mass number and an atomic number for alpha radiation. An alpha particle has 2 protons and 2 neutrons, which means it's got an atomic number of 2 and a mass number of 4. You might notice this is exactly the same as helium, but it will be a nucleus of helium in this case, and you need to be familiar with using that instead of the alpha symbol. So let's look at an example. I've got uranium with an atomic number of 92 and a mass number of 235, and it's going to decay into thorium plus our helium nucleus alpha particle. You know that the helium nucleus is an alpha particle, so that's going to have 2 and 4 as the atomic and mass number. And if we compare the left-hand side to the right-hand side, if the uranium nucleus has lost 2 protons, that means that the atomic number is going to go down by 2, which in this case means it goes from 92 to 90. The mass number has lost 4, so that goes down to 231. So we can fill in those atomic number and mass number for our new element, thorium. Beta is a little bit trickier. So a beta particle has a mass number of 0 because there's no protons or neutrons in it, but it has an atomic number of -1. And I'll explain why that happens in a second. You can also use a beta particle. Instead of a beta particle, you can use the symbol for an electron to represent it. It's the same thing. So let's look at an example. Let's take our carbon-14 from earlier, and that's going to decay into nitrogen. And then it's going to have a beta particle be emitted as well. Now, when the beta particle is emitted, we can see the mass number does not change. So therefore, the mass number of nitrogen can't change. So therefore, it's now 14. The atomic number, on the other hand, the atomic number of our beta particle is -1. So something plus -1 has to equal 6. In this case, that's going to be 7. So the atomic number is actually increased from 6 to 7. Now, the reason this happens, and this is really tricky to get your head around, is that inside the nucleus, a neutron has changed into a proton. It sounds like magic, but that has actually happened. Now, when that's happened, that means the atomic number has gone up by 1, but the mass number hasn't changed because the atomic number would go up by 1 for an extra proton, but down by 1 because it's lost a neutron. So the number of protons and neutrons hasn't changed, hence why it stayed at 14 in this case. Gamma radiation, you wouldn't find any nuclear equations with because it does not affect the mass number or the atomic number of our unstable nucleus. Radioactive decay is random. You cannot tell when an individual nucleus will decay, but we can use the idea of half-life to make predictions based on large numbers of nuclei. The definition for a half-life is the time taken for the number of nuclei to decrease by half. The number of nuclei could instead be the activity or the count rate. So if we look at a graph here, if I've got number of nuclei against time, if I wanted to find the half-life, I would take the number of nuclei at the start, in this case it's 1,000, I'd go down to half that, in this case 500, and I'd go along, read off the graph to see what the half-life is. That'll be the time taken for that to happen. Now we should notice every time the number of nuclei halves, so 500 to 250, 250 to 125, it should take the same amount of time to halve, so the half-life is constant. So in this way, we can actually make it all predictable. It's a random process, but we can predict for large numbers of atoms how many might decay in a certain time frame. So let's look at a couple of examples, because these are the kind of questions that can often catch people out. So what is the half-life of a substance that initially has 3,200 nuclei, and after 9 days, it now has 400 nuclei? So the first step is to figure out how many times it's halved. So 3,200 halved once is 1,600, halved again is 800, and halved again is 400. That means it's halved 3 times. So 3 half-lives have taken place in 9 days. That means that in 9 days, 3 half-lives means that 1 half-life is going to have a half-life of 3 days. In example 2, it says what percentage of atoms have decayed after 400 years if a substance's half-life is 100 years. So we've got to figure out after 400 years, if the half-life is 100 years, how many half-lives is that? So 400 divided by 100 gives you a half-life number of 4. So in 4 half-lives, we've got to figure out what percentage we get left after 4 half-lives. So 100 to 50 is 1 half-life, 50 to 25 is another, 25 to 12.5 is another, and 4 half-lives means it's halved 4 times down to 6.25%. Now this question is a bit sneaky. It doesn't ask what percentage are left, it asks what percentage of atoms have decayed. So therefore, if we do 100% minus 6.25, that means that 93.75% of atoms have decayed. For medical uses, a half-life of a few hours is quite common. The reason if it's too much longer than that, the radioactive source will be in the person for way longer than they're in the hospital, and too short means that they can't do any measurements involving it. Let's have a look at 3 different examples here. I've got 3 sources, uranium, potassium and carbon, and I've got their half-life. Now I have made most of these half-lives up just to make a point, but it could be any different elements given to you in your exam. So the question would ask, which source has the biggest hazard if you ingest it or if you eat it? Now to understand this, we've got to understand the idea of activity. On the previous part of the video, we looked at activity being number of decays per second. Now for this graph of number of nuclei versus time, the activity, number of decays per second, or the rate of decay, is going to be highest at the start where the gradient is really steep, and it's going to be lowest near the end where the gradient is more shallow. So actually the shortest half-life is going to be the biggest hazard because it has the highest activity, the highest number of decays per second. That's going to provide the biggest dose to the person if it gets absorbed into their body. Now, talking about hazards from radiation, let's talk about 2 really important key terms, which are contamination and irradiation. When something's contaminated, what it means is that there's an unwanted presence of radioactive material that's inside the object, material, or the person. On the other hand, irradiation refers to something being exposing an object or a person to nuclear radiation. Note that that does not make the item become radioactive, it's just being exposed to it. So an example of contamination would be swallowing a small amount of a source by accident, or potentially water from a power station leaks into the surrounding soil. The thing is now contaminated because it's got the radioactive material inside it. Irradiation, an example, would be pointing a radioactive source at someone. Not a good idea, but it does not make the person radioactive, it just exposes them to radiation. So generally speaking, irradiation would be less dangerous. Now to avoid these 2 things, if your teacher has shown you reactive sources in a classroom, they would take a number of precautions. They usually wear gloves to avoid the material getting on their skin and then getting inside them later. They usually use tongs to keep a big distance between them and the source, and they'll probably wash their hands after use for the same reason as they wear gloves. Now, other people in the room need to make sure they stand at least 2 meters away to reduce the chance of becoming irradiated, and the sources themselves need to be kept in a lead-lined box to prevent the source radiation leaking out from the box. You're only supposed to have the sources out for as long as you need them for. You don't want to leave them on the side of a classroom or a room any longer than you want to use them. Therefore, you are minimizing the exposure time to the class or to whoever you're showing them to. Now, despite these dangers, radiation is around us all the time in the form of background radiation. Background radiation, as the name suggests, is radiation that's around us all the time. We can't really do anything about it. It comes mostly in the UK from radon gas, about 50% from radon gas, which is from rocks, in particular areas like Devon and Cornwall that have a lot of granite. The other background radiation sources, some of them are artificial, so this would be from nuclear weapons fallout, usually from decades ago. This might be from nuclear power stations and also from medical sources. You also have a certain amount of background radiation from food and drink, from radioactive foods like bananas, quite famously, and also cosmic rays, which are rays from outer space, especially if you have a job where you're flying on planes a lot. Now, radiation dose is measured in something called millisieverts. Sieverts you don't need to know as the unit, but it's a good example of just being familiar with it so you don't get put off in questions. Now, millisieverts means 1,000 millisieverts is 1 sievert, or 1 millisievert is 1,000th. So it's a good opportunity for exam questions to test how can you compare different dangers with things like this. So for example, if we look at the different millisieverts of dose for each of these, we'll find that cosmic rays, for example, might have 1.6 millisieverts per year. We might find a banana on average has about 0.00098 millisieverts. That should say millisieverts, not sieverts there. And we've also got each of these will have different amounts of dose associated with them. Compare them to the dose for fatality, to die, that would be 10,000 millisieverts or 10 sieverts. So even though it's not great to have background radiation all the time, it is never going to be anywhere near enough to kill you, even if you have quite a few x-rays. So we'd be careful with it, but it's not much in comparison to what would be needed to actually kill someone. Okay, the last part of this section of the video is all about fission and fusion, which is only if you're doing triple science or separate science. You do not need to worry about this if you're doing combined science. So let's look at nuclear fission first of all. Make sure you're spelling this correctly. So nuclear fission, there are two types. There are spontaneous and induced fission. Nuclear fission is defined as the splitting of a large nucleus into two smaller nuclei, which releases neutrons and energy in the form of gamma rays. Now, spontaneous fission is very rare and it would occur naturally in fuel like uranium in the ground. Much more likely is induced fission, which means it has happened artificially. Now, this occurs when uranium or a plutonium nucleus gets hit with a slow-moving neutron. The slowly moving neutron is absorbed into the uranium. It does not pass straight through, but it gets absorbed. The uranium will then split into two. Now, the fragments it splits into, you don't need to be familiar with, but it will be two similarly sized elements about half the size of a uranium nucleus. Now, when that happens, it will release between 2 and 4 neutrons. When those neutrons then carry on going, something called a chain reaction can happen. If they encounter 3 more uranium nuclei, the same process can happen again if they're absorbed by the uranium nuclei and then the uranium nuclei split again, releasing neutrons. So you might have, just from 2 different reactions, you have got 9 neutrons, and you times by 2 or 3 each time, there are lots and lots and lots of energy released, which is what might result in a nuclear bomb or a nuclear explosion. Now, we can harness this in a nuclear power station to use it usefully. We do not want a nuclear bomb. So to be able to do this, we need to have a few different things in our nuclear power station. So control rods are a big part of a nuclear power station because they allow us to control the rate of reaction. They absorb the neutrons, so take in the neutrons, so they reduce the rate of fission. They reduce the chances of those neutrons going on to cause more fission. A moderator is another example of something in a nuclear power station. This slows the neutrons down so they can actually be absorbed by uranium in the first place. You'd also have thick concrete shielding, and we'd need to know in a nuclear power station, the rest of the power station is identical to what you'd find in a coal power station, for example. You have heat that drives steam, heat water drives steam, which makes a turbine turn, and then you have a generator to convert it to electricity. Nuclear fusion, on the other hand, is the opposite process. Fusion is the joining together of 2 light nuclei to form a heavier nucleus. And as that happens, a small amount of mass is converted into energy. This is given by the equation E = mc squared, which isn't on the GCSE spec, but sort of helps explain how those two things are linked. Now, nuclear fusion is very difficult to make happen because you've got 2 hydrogen nuclei, the lightest elements. They both have a positive charge. So to make it fuse together and turn into a new element of helium, you're going to need really, really, really high temperatures and pressures. This is so the particles have enough kinetic energy or enough speed to overcome electrostatic repulsion so they can come together in the first place. And that's the end of the topic on atoms and radioactivity. I hope you found that really helpful. Make sure you revise this topic as it's one of the trickier ones that comes up on a lot of papers.